Look at the Earth from orbit, and you see a continuous, chaotic engine of moving air and moisture. There are no borders in the atmosphere. But to study the climate scientifically, we have to impose order on that chaos. We need a way to snap those fluid, ever-changing weather patterns into distinct, rigid categories with hard boundaries. In 1918, climatologist Vladimir Koeppen provided the solution, developing the most widely used system for classifying global climate. It is a strictly empirical system. Rather than attempting to group climates by their underlying causes, Koeppen built his entire framework around observed historical data. To map the planet, he realized we had to translate raw meteorological inputs, temperature and precipitation, into a universal structural syntax. Koeppen started with a foundational axiom: the natural distribution of native vegetation mirrors physical climate boundaries. Decades before global satellite monitoring, the flora of a region functioned as a permanent, macroscopic weather station. The plants that managed to survive in a given area reveal the exact climatic thresholds of that environment. A dense, highly biodiverse equatorial canopy, for example, demands specific, extreme thermal and moisture parameters to exist. Contrast that with a landscape where annual precipitation is completely inadequate to support plant growth. By observing these distinct biomes as a proxy for the raw data, Koeppen engineered an alphanumeric code capable of organizing the entire biosphere without relying on abstract numbers alone. The matrix begins by dividing the world into 5 primary macroscopic groups, labeled with capital letters A through E. There is a strict structural asymmetry here. Groups A, C, D, and E are defined exclusively by absolute temperature thresholds. Group B is the solitary exception. Group A represents the tropical humid climates. This is the baseline equatorial zone, where the average temperature of the coldest month never drops below 18 degrees Celsius. Group C is the warm temperate, or mid-latitude zone. Here, the coldest month falls below 18 degrees, but hits a floor at -3 degrees Celsius. Drop below that -3 degree freezing threshold, and you enter Group D, the cold snow forest climates of the higher latitudes. Finally, Group E isolates the polar zones. In these extreme environments, the average temperature for every month remains strictly below 10 degrees Celsius. There is no true summer. These 4 capital letters alone establish the absolute thermal bands, mapping the Earth from the equator out to the poles. That leaves the outlier, Group B, the dry climates. Group B ignores the established temperature rules because aridity spans massive latitudinal ranges, occurring anywhere from 15 to 60 degrees from the equator. The defining metric here relies on a dynamic calculation. Group B is triggered only when a region's potential evaporation exceeds its actual precipitation. This moisture deficit explains why these climates correlate so closely with areas of subtropical high pressure, or deep continental interiors blocked off from maritime winds. Group B acts as a specialized logic gate. The moisture deficit dictates the physical biome, overriding whether the desert itself is freezing or boiling. A massive macroscopic temperature band lacks precision. To accurately describe a climate, the system encodes the seasonality of precipitation using a secondary layer of lowercase letters. An F indicates an environment with no dry season at all, while an M denotes a monsoon climate marked by short, extreme wet and dry fluctuations. Then we have the specific drought modifiers, W for a winter dry season and S for a summer dry season. When we apply these to the primary groups, the logic snaps into focus. Combine Group A with an F and you get AF, a tropical wet climate with constant moisture. Swap that modifier to a W and it becomes AW, a tropical wet and dry climate defined by a severe seasonal drought. Appending a single lowercase letter transforms a broad latitudinal band into a precise seasonal profile. That profile dictates whether a dense forest or a sparse grassland takes root in the soil. The system adapts when confronted with the extremes. Groups B and E abandon the lowercase seasonal modifiers entirely, utilizing specialized capital letters to measure severity. Group B branches into 2 stark categories. S stands for steppe, a semi-arid zone supporting sparse grasslands. W stands for desert, indicating absolute aridity with zero effective moisture. In a W classification, the environment experiences high diurnal temperature ranges and intense, ineffective thundershowers that fail to build any lasting soil moisture. A tertiary lowercase letter is then added to establish the thermal floor of these deserts, an H for a hot subtropical zone, or a K for a cold mid-latitude desert. The polar group E follows a similar severity split. ET represents the tundra, an area where a brief seasonal thaw supports shallow permafrost vegetation. Contrast that with the absolute limit of the system, EF, or ice cap. Here, temperatures never breach the freezing point, and perennial ice accumulates year-round. These deviant subroutines allow the matrix to accurately classify the harshest biomes on Earth using just 2 or 3 keystrokes. When assembled, the complete Koeppen matrix functions as a unified algorithm. We can reverse engineer the process with a real-world test. Take a mid-latitude coastal region like Central California. The region has mild winters, placing it squarely in Group C, but it also experiences uniquely dry, hot summers. The algorithm processes those variables and outputs CS, instantly defining the classic Mediterranean climate. A Koeppen code acts as a highly compressed file containing a region's entire meteorological identity and biological potential. But the parameters Vladimir Koeppen observed in 1918 belonged to a specific moment in time, and the global climate is not static. Geologic and ice core records show us that the Earth naturally alternates between glacial and interglacial periods. However, this historical variance is now colliding with an anthropogenic effect. The rapid concentration of greenhouse gases is actively warming the troposphere, forcing the system out of balance. The numerical thresholds for Koeppen's letters remain fixed, but the geographic zones they describe on the map are actively migrating. We see this physical migration in real time through the rapid, accelerating recession of high-altitude glaciers across the planet. Koeppen's empirical map provides the scientific baseline against which we measure the accelerating destabilization of our biosphere.